So in respondent conditioning, we learned about generalization and discrimination that can show up whenever you learn a new association, something that makes you elicit a conditioned response to a conditioned stimulus, right? Generalization means that as sort of a side effect of that respondent conditioning, you show the conditioned response for other stimuli that just happen to be somewhat similar to the CS you learned. Whereas discrimination means you don't have much generalization, like your conditioned response pretty much only happens for the exact conditioned stimulus itself. But that was for respondent conditioning. What about for operant conditioning? You may remember this example I gave for positive reinforcement, back when we learned those contingencies. We reinforce a toddler for saying please, right, at the table when dessert is being served for dinner or something like that. And if they say please, if that's their behavior, then the outcome is the parent gives the toddler dessert. We add a nice stimulus. That's positive reinforcement, right? But that doesn't mean the toddler starts saying please all day long, nonstop, right? It might only happen in this specific situation in the future, even if you'd want it to generalize, right? It might only happen in that one situation. Or for negative reinforcement, I gave the example of hitting the snooze button on an alarm clock, a behavior which removes a stimulus, it removes something annoying. That success increases the probability of that behavior of hitting the snooze button in the future, but only when the alarm goes off, not at random times throughout the day. I don't stand up after finishing my lunch and go press the snooze button for no reason, right? The behavior only happens in a specific context. Likewise, for the example I gave of positive punishment, where a ticket or a yelling stimulus is added after you do the behavior of speeding on the highway, I said, in the future, you do not speed as much on the highway, but your city driving might not change. It might even be specific to just that one stretch of highway where you don't speed anymore. Or perhaps you do stop speeding in any context at all, right? Perhaps it does generalize a lot, but that's something we'd have to look for. So likewise, for the negative punishment example I gave of having your license and driving privileges removed for doing the behavior of driving in the situation where you're drunk, I said the result is that in the future, after drinking, you don't drive. But presumably the punishment doesn't make you stop the behavior of driving across all contexts, like even when you're sober. Ideally, it just makes you stop the driving behavior in the contexts where you've been drinking. So in all these examples of operant conditioning that we learned before, this little detail I'm pointing out is about generalization or discrimination. Your behavior changes through operant conditioning, but the behavior change may be specific to the context or circumstances, which would be operant discrimination, or it may sometimes generalize to other contexts and circumstances, which would be operant generalization. So we're going to discuss both of these in the next few videos, but let's start with operant discrimination, telling things apart, acting differently to different stimuli. So this is usually described as stimulus control, when you behave one way in the presence of a stimulus and another way in its absence, or to a different stimulus. What we're talking about is stuff we've run into this before, right? We're talking about basically stimuli like an SD, a discriminative stimulus, or an S delta, or like that S aversive, right? An aversive stimulus that we learned. That if these stimuli are present, right, they might increase or decrease the probability a behavior will occur in the current circumstances. So it's called stimulus control because in some sense, the stimulus is controlling what you do, controlling your response. The environment is influencing your behavior. For example, a stop sign stimulus controls your braking behavior. It makes it more likely, right? It's not like it's guaranteed. It doesn't mean that you can't do something else, right? You might decide to run through the stop sign, but it makes that behavior more likely. So it's influencing or controlling your behavior. A stop sign is an SD, a discriminative stimulus, for the braking behavior. We'd say it sets the occasion for braking, makes it more likely. Likewise, the telephone ringing controls the behavior of picking up the phone and saying hello. It's an SD for picking up the phone and saying hello, but a different stimulus like the doorbell ringing, that doesn't make you pick up the phone. It doesn't set the occasion for that behavior because in the past, you never got reinforced for that behavior in the context of the doorbell ringing. That's the idea of stimulus control. Or another example might be if you always eat when watching TV, like that's a habit for you, your eating behavior is controlled by the stimulus of TV being on. then we'd say TV being on is an SD. It's a discriminative stimulus for eating behavior. It sets the occasion. It makes eating more likely, just having the TV on in front of you. You may simply experience it like from the first person perspective. You may experience it as just, I'm having a craving, or I tend to have cravings for food when I sit down in front of the TV. You experience it as something you do kind of automatically, as a habit. But what's happening is stimulus control. So what we're talking about here, when some stimuli make you do the behavior and other stimuli don't, is really just discrimination. It's responding differently to different stimuli. In other words, you can tell stimuli apart, and only specific stimuli control your behavior. For example, a red traffic light is a discriminative stimulus for braking behavior, making it more likely, whereas a green traffic light is an S delta for braking behavior, making it less likely. You don't want to hit the brakes when you're in the middle of an intersection, right? At the same time, you could say a red light is an S delta for pressing the accelerator in your car, right? It makes it less likely to press the accelerator if you see a red light. The red light can control multiple behaviors simultaneously, right? The red light would make braking behavior more likely, but would make accelerator pressing less likely, right? It can have multiple functions, the same stimulus. Now, previously with respondent conditioning, we saw that discrimination and generalization, they're opposites, right? If you have a lot of discrimination, you don't have much generalization, and vice versa. And the same thing holds true here with operant conditioning. Discrimination would mean you're good at telling apart the stimuli. You only respond to the SD. You only brake for the red light. Generalization would mean you respond to a variety of stimuli that are different than the SD. So an extreme example of generalization would be if you press the brake in your car for all lights, whether red or yellow or green or a brand new blue one that shows up. In that case, you don't really discriminate the colors, right? So obviously in real life, we usually want drivers to discriminate different traffic signals. Discrimination can be useful, but we'll see generalization can also be useful for some things. We need both. Now, imagine you want a person or a pet or your child or whatever to behave differently depending on the circumstances. Like you want your guard dog to attack strangers but not familiar people. Or you want your toddler to poop when they're sitting on the toilet but not when they're sitting on a plastic chair in the living room. In other words, you want discrimination. So you can specifically, if you want it, you can train discrimination. You can make it more likely by using what we call a differential reinforcement procedure. What you could do, for example, is just kind of alternate between a reinforcement contingency for a while and then an extinction contingency for a while. So first you might do like 10 minutes where one of the stimuli is present. We'll call it the SD. And during that time, the desired behavior is reinforced. Like for a rat in a Skinner box, you'd turn on a blue light, and during that time, pulling a lever gets a treat. Blue light on, pull the lever, you get a treat. Then, though, you'll spend a while in an extinction condition using a different stimulus. So you might do 10 minutes where an S delta stimulus is present, during which time the behavior doesn't pay off. It doesn't get reinforced. Like instead of a blue light, now maybe you're turning on a yellow light. And during that time, pulling the lever doesn't work. Or perhaps even pulling the lever leads to getting shocked or something like that. And you just kind of rinse and repeat this procedure for a while, alternating these two contingencies over and over again for a while each. That is a differential reinforcement procedure. Eventually, they'll pull the lever only when the blue light is on. They're learning to discriminate the colors, discriminate those two stimuli, and only respond to one stimulus, to one situation. So you'll get discrimination out of this. You can actually use the same idea, but alternating between two different schedules of reinforcement. Like the blue light might mean that lever pressing leads to a lot of treats, like a really good schedule of reinforcement. And maybe the yellow light means lever pressing leads to only a few treats, like a really crappy schedule of reinforcement. As they spend a while, as you go back and forth, they get experience with both of these. They'll learn the contingencies, right? They'll start responding more when the blue light is on. So we'd say the light stimulus comes to control their behavior in that circumstance too. Now, when we do this, alternating back and forth between different contingencies or different reinforcement schedules, it's called using multiple schedules. Or for shorthand, we might write it as just MULT, M-U-L-T, short for multiple schedules. Okay. So for example, alternating FR10 for an hour, fixed ratio 10 for an hour when like the red light is on, then we might do extinction for an hour when the green light is on. So during extinction, they do the behavior, they press the lever, nothing happens, right? We could describe that in shorthand as a molt FR10 extinction. So multiple schedules, and then we give the schedules after that. The FR10 is one schedule, the extinction is the other schedule, and the molt tells people when they're reading this that we're switching back and forth between those two. We're doing each one for a while and repeating it. So we're alternating a fixed interval 2-minute schedule for 1 hour, like maybe it starts when a high-pitched tone happens. Then we do a fixed interval 3-minute schedule for an hour. And that one might start when a low-pitched tone happens as the signal, as the stimulus, right? We would write that as a molt FI 2-minute, FI 3-minute. Now, just as a reminder check, which of those two schedules will let the individual get the most reinforcers? Pause the video a second if you're not sure and think it through. So the FI 2-minute actually gets you more reinforcers because it means there's only a 2-minute delay before you can earn another treat. Whereas in an FI 3-minute, there's a 3-minute delay each time. So even if you're great at telling time, you just can't earn as much on the latter schedule. All right, another example, though this one might seem kind of weird, would just be alternating like a VI 60-second schedule with another VI 60-second schedule. Like for 5 minutes, a blue light is on and you do that schedule. Then for 5 minutes, a yellow light is on and you do that same schedule. Then repeat that back and forth, back and forth. The reason we might do that, though, is we could kind of change one of those schedules afterwards so that it's no longer equal and see how the individual's behavior changes as a result. So we'd kind of have a built-in control condition, basically. Now, to test your understanding, maybe pause the video a moment here and see how you would describe the following procedure in everyday language. The molt VR30 EXT. So basically what this one would be is presenting some sort of signal like a particular light or sign or tone, and during that hour, you get rewarded every 30 or so times that you do the behavior, right? It's variable, but every 30 or so times. But then a different signal comes on for an hour, like a different light, and during that time, doing the behavior gets you no reward. That's the extinction, the EXT. Then you go back to the first signal for an hour and the behavior gets rewarded again for roughly every 30 behaviors, and we go back and forth, back and forth. Eventually, we would expect them to do the behavior only when that signal is present and not when the other signal is present. Okay. Well, in this video here, in the next one, we're going to get into a bit more detail about measuring and applying operant discrimination.